Why have we all admired the fluid, graceful movements of highly skilled performers in various sports? Well, our reasoning is biomechanics provides a foundational understanding of mechanical principles and their applications in analyzing movements of the human body. This can answer the questions for us as to why and how athletes like Harper Murray are able to perform unbelievable skills at a high level so consistently. The topics we will touch on are height and vertical jump, vertical velocity, center of mass, impulse, ground reaction force, Newton's second and third laws, angular velocity, momentum, torque, and planes of motion. Throughout this video, we will introduce the phases of specifically an outside volleyball spike. These phases include the approach phase, propulsive phase, arm swing and follow-through phase, and the landing phase. We will break down and analyze the biomechanics of each phase as well as the variations of a hit that can be performed. We will also touch on injury prevention during the landing phase of a spike. The first phase we'll begin talking about is the approach phase. Your center of gravity is relevant during a volleyball approach because it is key to converting horizontal speed into vertical height. A highly important step in this approach is the penultimate step, which is known as the second to last step. This is a long, forceful stride that lowers the hips to convert horizontal speed into vertical power. By lowering your center of gravity in the penultimate step and using the final step to efficiently transfer forward momentum into upward momentum, you can jump higher and more powerfully. Maintaining control of your center of gravity throughout the approach is crucial for stability, coordination, and achieving an effective jump. The whole approach run process showed us that the first step was small, the second step was large, and the stride gradually increased. The second step has the largest amplitude, accounting for 52% of the total run-up distance, and the maximum speed of the run-up is also generated in this step. In the same way, the athlete can gradually increase the speed of the center of gravity to facilitate the transition between the two steps. The momentum a player builds during their approach steps is equal to the kinetic impulse they generate. According to the law of kinetic momentum, also known as the impulse-momentum relationship, the impulse produced by applying force over time causes a change in momentum. So, the more forceful and well-timed the approach steps are, the more momentum the player carries into the jump. This horizontal force that is transferred into vertical force, therefore, this approach is decisive in volleyball success in the real aspect. Timing the hit takes practice. The approach should be delayed long enough so that the hitter is able to generate a great deal of speed and power, which will generate an explosive jump. This allows the hitter to reach the ball at peak of the jump and contact the ball at the highest possible point. Within the approach phase, variables such as movement time, power, starting speed, and jumping distance play a large role in contributing to the explosive power of the legs, which are required during the propulsive phase. These variables also key into the four-step approach that gives the player more forward momentum, which converts into vertical lift during takeoff. Next, we will talk about the propulsive phase. When first addressing the propulsive phase, we begin to look at Newton's second law, which is simply force equals mass times acceleration. The more force the athlete applies to the ground, the more their body accelerates upward. This means that when a volleyball player pushes harder into the floor with their legs, they create a greater acceleration of their center of mass, which therefore propels them vertically. Newton's second law explains that because the weight of the athlete is consistent, the only way to accelerate upward faster and jump higher is to generate more muscle force against the floor. Jump height depends mainly on how fast the center of mass is moving upward at takeoff. Therefore, the greater the upward velocity, the higher the jump. Athletes maximize this by producing strong force with good technique, proper timing, and efficient approach while all working against gravity's downward pull. The muscles generate more force when they contract more slowly, which is why the counter movement and the arm swing help by briefly showing the leg's contraction and increasing force production. Within these leg muscles, we see slow twitch fibers which support controlled, forceful movements, while fast twitch fibers contribute to producing the explosive power needed for a higher jump. Muscles generate the greatest force when at optimal length, and in a jump, this involves the hip flexors, knee extensors, and ankle plantar flexors. The force produced by these muscles directly drives takeoff velocity by accelerating the center of mass upward. Now to break it down. Hip extension occurs during push-off. This is used to drive the body upward using the gluteus maximus and the hamstrings to assist hip extension. Next is knee extension. This is a major contributor to upward force during the propulsive phase as the quadricep muscles such as the vastus lateralis, vastus medialis, vastus intermedialis, and rectus femoris are being used. Next, we see ankle plantar flexion. During the final propulsion from the ground, the gastrocnemius and the soleus are being used to generate the final force. In addition, the core muscles play a vital role in trunk stability and energy transfer via the rectus abdominis, obliques, erector spinae. Trunk rotation increases the acceleration of path of the hitting arm. The arm swing muscles used to assist jump height indirectly have shown to increase vertical jump by 19 to 23%. The muscles involved include the latissimus dorsi, deltoids, pectoralis major, and triceps. The reasons for this improvement are an increased center of mass due to the elevated arms at takeoff and a decrease of contraction velocity of the leg muscle, which leads to an increase in the muscle force due to the force-velocity relationship. Lastly, it is important to know proper knee and hip angles help place muscles in this strong position in the propulsive phase. There are a few main joints that are used during this phase, and those include the acetabulo-femoral joint, which is considered to be a third-class lever, is also known as the hip joint, and it is controlled by the gluteus maximus during this phase to achieve hip extension when the athlete begins the vertical jump. Next is the tibiofemoral joint and the patellofemoral joint, which are considered to be third-class levers. The tibiofemoral joint is known as the knee joint. During this phase, the tibiofemoral joint is controlled by the quadriceps muscle group. Lastly, the tibiotalar joint, which is considered to be a second-class lever, is known as the ankle joint. It is controlled by the gastrocnemius and soleus muscles to help propel the body off the ground.
Next, we will be talking about the arm swing and follow-through phase. During a volleyball spike, the arm swing moves through 4 phases: the approach, arm cocking, acceleration, and follow-through. The major shift happens when the shoulder reaches maximum external rotation, initiating the fast uncoiling that drives the arm forward. At contact, the elbow stays slightly flexed at about 34 degrees in a crossbody spike to maintain control, reduce joint stress, and keep the arm fast through the hit. The shoulder is positioned high and lateral at roughly 130 degrees of abduction, maximizing reach and force transfer, while strong torques occur at both joints. The non-hitting arm assists with balance and alignment in the air, enabling a clean, fast arm path. Overall, spike power relies on rapid rotation, controlled elbow positioning, and coordinated whole body mechanics. During the spike, the muscles and joints are crucial to create and transfer power. The lower body muscles, especially the quads and gluteus maximus, push into strong extension during takeoff to turn the athlete's horizontal speed into vertical lift. The trunk muscles rotate the torso in the transverse plane, giving the arm swing much of its rotational power. The main shoulder movers, the anterior deltoid, pectoralis major, and subscapularis, create internal rotation and horizontal adduction during the acceleration phase, while the rotator cuff keeps the shoulder joint stable during contact and as the arm slows down. The triceps finish the elbow extension during the swing and then work eccentrically to control the arm after the ball is hit. Wrist and forearm muscles add the final burst of movement that increase hand speed and improve ball control. Important joint actions include ankle, knee, and hip extension in the sagittal plane for the jump, trunk rotation in the transverse plane, shoulder internal rotation and horizontal adduction, elbow extension, and wrist flexion and extension. Overall, the spike uses all 3 planes of motion: sagittal for jumping, transverse for rotation, and frontal for guiding the arm path and maintaining stability. When breaking down the striking mechanics of a volleyball spike, rotational power is the first major theme, and studies consistently show the same pattern. The movement starts with trunk transverse rotation, which generates the majority of the angular momentum that ultimately drives arm swing velocity. Shoulder internal rotation rapidly increases the angular momentum of the forearm and hand just before ball contact. Hip rotation aligns the pelvis so the trunk can rotate in the right direction and at the right time. Once the hips and trunk are set, the body follows a smooth proximal to distal sequence, from trunk to shoulder to arm to hand, where large segments build angular momentum first and smaller distal segments accelerate last. When the sequencing is correct, overall swing velocity and power increase significantly. As the hitter moves into the contact phase, the spike begins with converting horizontal momentum from the approach into vertical impulse during the jump, positioning the athlete optimally in the air. After takeoff, energy transfers through the kinetic chain. from pelvis to trunk to shoulder to elbow to wrist to hand. All of the stored momentum converges at ball contact, which is the final point of transfer where accumulated energy moves from the body to the ball. Each segment must accelerate and then decelerate in the proper order. Errors such as an early arm swing or delayed trunk rotation reduce ball velocity and increase stress at the shoulder and elbow. When looking at the forces acting on the ball's exit speed is primarily determined by final hand velocity. The impulse applied to the ball comes from the rapid deceleration of the hand as the ball accelerates forward. Wrist flexion, also seen as the wrist snap, adds additional linear velocity and helps produce topspin. As the hand wraps over the ball, friction combined with wrist and finger flexion produces spin. Once the ball leaves the hand, topspin may increase downward force, sharpen the ball's trajectory, improve control, and make the ball drop faster into the court. Now we will look at the follow-through phase. Right before impact, the arm reaches its max external rotation. The shoulder sits at about 130 degrees of abduction, and the arm moves from a more open position toward horizontal adduction, so the hand is lined up for a clean hit. At contact, the elbow is extended and the forearm is pronated to different degrees depending on the shot. This creates sharp spikes in internal rotation torque that the pectoralis major, latissimus dorsi, teres major, and subscapularis have to handle to keep the arm moving and stop the ball from completely slowing the swing down. The wrist snap is powered by the wrist flexors and pronators, and it helps create a steeper, more controlled attack angle. After contact, the arm quickly comes back across the body and drops out of that high abduction position to absorb the forces created at the end of the acceleration, helping to protect the shoulder. This entire motion includes the shoulder joint, scapula, clavicle, humerus, radius, and ulna working together through different motions, rotations like internal and external rotation and pronation, sagittal plane actions like elbow extension and wrist flexion, and frontal plane changes like adjusting abduction. Faster humeral rotation boosts ball speed by around 5%, and techniques that build higher hand speed right before impact consistently produce stronger spikes. Altogether, this phase plays a major role in determining the spike's final power, its spin, its trajectory, and how safely the shoulder handles the forces of the hit.
During the landing phase of a volleyball spike, the athlete's body is moving rapidly back toward the ground, and gravity increases their downward momentum. That momentum has to be absorbed on impact, which creates very large landing forces. The ground reaction force pushes up hard to slow the body down, and that upward push is what stresses the joints. In fact, the landing forces and loading rates are usually higher than those during the takeoff, which is why poor or high force landings are directly linked to increased injury risk. These high peak forces can overload the lower limb joints and contribute to injuries like ACL tears and patellar tendinopathy, which are both common in volleyball. Several factors influence how much force an athlete absorbs when landing. Surface stiffness matters. Landing on soft surfaces like sand, the athletes experience lower knee stress and fewer patellar tendon issues than indoor players. Shoe stiffness also affects the forces produced during impact. Technique plays a major role as well. Landing softly with good knee bend reduces force, while stiff or locked landings increase it. Finally, volleyball players often land differently depending on the play and set. Research shows that spike landings are often asymmetric, and athletes hitting fast sets are more likely to land on one foot, which is significantly increasing knee joint load and injury risk. There are various ways to aid in injury prevention for volleyball athletes. First, implementing correct landing techniques can help reduce the risk of lower extremity injuries. Also, strengthening the knee extensors through eccentric exercises is an effective strategy for preventing patellar tendinopathy. Also, performing repeated eccentric contractions during drop jumps may produce a stronger protective effect against injuries relating to landing. And lastly, plyometric training incorporating dynamic stabilization exercises could reduce the impact forces and incidence of knee injury in female athletes.